This is problem number 2 for exam 3 review. So the hybrid pi is shown here. It's given R pi 1 is 50K, GM2 is 50 milli, and beta is 50. So from these, R pi 2 can be determined as beta over GM2, which is 1K, and GM1 can be determined as beta over R pi 1, which is 1 milliamp per volt. So R in needs to be found, R out needs to be found, and V out over V sig. So this is 50K. GM1 is 1 milli. R pi 2 is 1K. And GM2 is 50 milli. So let's start with Rn. So Rn can use the resistance reflection rule. It's said to just ignore the source and then take the pathway in. So we're in the emitter and everything in the base would be reflected. So Rn is equal to 4K plus, and then all of these would be plus, R pi 1 plus 100K plus 100K, all of that divided by beta plus 1. Which equals 8.9K. Not very good. You want a much higher Rn value. For R out, looking in at the top of the BJT, this is going to look like an open. So the pathway from here to ground, I have a split, so this split is in parallel with this split. I go through here and I have another split, but this is just floating, so I ignore it. So in this branch, it's 2K plus 3K plus 1K. All of that is in parallel with 2K. They converge, and then it's plus 6K. So R out is equal to 2K plus 3K plus 1K. All of that in parallel with 2K plus 6K. So that gives a value of 7.5K. Again, not great. You want usually an R out less than 1K. So I'm going to write this up here as 7.5K. So next, finding V out over V sig. I'm going to start with a V out equation. So I have a current here, and it goes in, it splits, and then it converges again, and that same current goes out. So I can use a current divider and find the current in this branch, and the current down here is going to be GM2 V pi 2. So to find this current up here, I'm going to find V out is equal to the current divider, GM2 V pi 2. The branch opposite is going to have 3K plus 1K, so 4K, over the total is going to be 4K plus 2K plus 2K, so 8K. This 5K does not affect the current divider in any way. You already know the current going through it, but it doesn't affect the division of the current. So this is I. I'm going to take it times 2K, and that's going to be the drop here. And then again, I have another negative, so I'm going to add on to this, a negative GM2 V pi 2 times 6K. So multiplying these out, they're both in terms of V pi 2, so I can get a value of negative 350 V pi 2. So now I need to find an equation for V pi 2, which is located across here. This goes to ground here, so V pi 2 is across R pi 2, but note that it's also, because it goes to ground here and here, these two are in parallel. So I know the current going through them, they're in parallel. I can again use a voltage or a current divider. So V pi 2 is equal to a minus GM1 V pi 1 times 2K, and this was 1K, in parallel with 1K. Oh, that's the voltage. So combining these two into one, I can find the voltage at this node, or I can use a current divider and then multiply it to get the same equation. So this ends up being a minus 0.667 V pi 1. So I have VO is equal to a minus 350 V pi 2, and V pi 2 is equal to a minus 0.667 V pi 1. So now we need an equation for V pi 1. So looking here, if I use the resistance reflection rule to get rid of this, I can just do a voltage divider. The polarity is going to be, there's a positive that's the closest sign to the negative, so they're going to be opposite. So V pi 1 is going to be a negative V sig times R pi 1 over the summation of all of the resistors. So 200K plus 4K. And minus 0.110 V sig. So now I plug this value back into here and plug this value back into here. And I can achieve VO minus 350 times a minus 0.667 times a minus 0.110 V sig. To get V out over V sig, I just divide that V sig, and I end up with a value of a minus 26 volts per volt. And that is my answer.